In the last lecture, we were looking at the Hill's equation, and then we ended by looking at how Hill interprets cooperativity, and we are also going to, or rather, we are saying that in Hill's equation, which is log of fractional saturation all over 1 minus fractional saturation against the log of ligand concentration. Okay, so we say that the intercept will give you the log kb, and then the n, which is the slope, will give you the Hill's coefficient, of which some views will interpret it as the number of sites. When you round it up as a whole number, it can give you the number of sites on the protein. It gives you an idea of the number of sites. But there are situations that arises where we cannot comfortably use it as the n as the number of sites, but that n gives an interpretation of the type of cooperativity that is going on. So we say that when you make a plot, the plot is a sigmoid plot. Okay, and how you actually calculate your slope is that you make a tangent, the lines you see on red. Okay, that tangent from the top and from the bottom. Okay, then you look for the most part of the plot that is linear, and you draw a line to meet those two tangents. Now that line, the one in green that you have drawn, is what you're going to find the slope, and that slope will give you your h, which is the Hill's coefficient. Okay, and we say that what the coefficient means is that if that coefficient is equal to 1, it indicates independent binding. When we talk about independent binding, we are saying that the sites are not interacting. Okay, that's why number one, we can't use that n as the number of sites, because it shows you that those sites are not interacting, or that it has only one binding site. Now when it is greater than 1, the h is greater than 1, is showing you a positive cooperativity, and when it is less than 1, it shows you negative cooperativity. Okay, some people goes ahead to look at h minus 1. If it is 0, you have independent binding. It is above, greater than 0, it has a positive cooperativity. If it is less than 0, it's negative cooperativity. So, but the most important thing is that you should know what h is, and you should interpret it based on what your own h is. Now let's look at the other equation. Now, Ade is just saying that cooperativity must not be complete or total. Okay, that the binding is sequential. So Ade is querying that P2 plus 2 for a protein with 2 binding sites, that P2 plus 2L, having a binding constant that to P2L2, that's not actually what it's supposed to be. Ade believes that they should be stepwise binding. The first site should be occupied by the KB1 before the second site is being occupied. Now, the KB1 and KB2 is known as apparent binding constants. Okay, now KB1 is equals to P2L all over P2 multiplied by L. So you can always calculate P2L to be equal to KB1 multiplied by K2L. Now, for the second apparent binding site, which is KB2, the is equal to P2L2 all over P2L multiplied by L. So P2L2 will be equals to KB2 multiplied by P2L multiplied by L. So you have to substitute P2L. Now, if you substitute that in the next equation, okay, you're going to have that P2L2 is equals to KB2 multiplied by KB1 multiplied by PL, then multiplied by L raised to power 2. Now, there are things we must understand, okay? Now, we look at the free sites or the free proteins, and we look at the bound proteins. Now, for the site, remember this site, have a way of interacting, the first site and the second site. So when we talk about free sites, there are two free sites in the free protein, and there is one free site on the bound protein. Okay, so those are the free sites. Now, for the bound protein or the bound site, there is one bound site in P2L, and there are two bound sites in P2L2. That is where the 2 you're seeing in front of P2 and the 2 you're seeing in front of P2L2. So when we talk about the total number of sites, okay, or total number of protein, we say it is the free protein plus the bound protein. So for the total number of sites, you see we have 2P22 in plus PL for the free protein, for the free site, and then for the bound site we have 2PL and then 2PL2. So when you summon it, you're going to have this, and you factorize, you're going to have 2 into P2 plus P2L and then P2L2. If you're writing this thing down, it will help you make a lot of sense. Sorry, this I'm using can't indicate, but I'm still working on it. Now, fractional saturation, which is bound protein over the total protein. Okay, so now anywhere we are seeing P2PL, we are going to substitute our KB1, PL2, and PL. And then anywhere we are seeing P2L, we are going to equally substitute this. Okay, so if y equals to the equation below, when you substitute, you will have y by which the fractional saturation is all this. So P2 is common in all of them. You can cancel all the P2s. If you factorize, you cancel. In class, we are going to show that. Now, so we are left with the fractional saturation is KB1L plus 2 into KB 2 KB1 L raised to power 2 all over 2 into 1 plus KB1 L plus KB2 KB1 L raised to power 2. Now, we have to look at the relationship between these implicit binding constants, that's the K1 or the apparent binding constant, the KB1 and KB2, with the explicit binding site KB. Okay, now there is an established equation in which the relationship is done. For instance, that equation is that KB1 is equals to KBI is equals to n minus I plus 1 all over I KB. Now, where n is the number of sites and I is the step of binding. For instance, you have KB1 for the first binding of L, that's the first step, and KB2 is the second binding. Okay, so if you calculate that, you will see that KB1 for a protein with two sites will be equal to 2 KB, while KB2 will be equals to half KB, which means that the binding of the KB2 is lower than KB1, but that is the established equation. So if we have that, we are, instead of having our KB1 and KB2, we are going to be establish this in terms of KB. Okay, so anywhere we have KB1, we will put 2 KB. Anywhere you have KB2, you will put 1 over 2 Kb. So if you do that, you're going to have that the fractional saturation will then be 2 kBl plus 2 times half Kb times 2 Kb multiplied by L squared, okay, all over 2 bracket 1 plus 2 kBl plus half Kb times 2 kBl raised to power 2. So the fractional saturation is given as this when you open the bracket, and it will give you this. Okay, now if you factorize y, you're going to have 2 kb plus l all brackets 1 plus kbl all over 2 into 1 plus kbl all squared. Okay, 2 can cancel out, and then you will still come back to this equation in red. And this equation, the equation before that actually will give you the added equation for a protein with 2 sides. You can do for the 3 sides, you can do for the 4 sides, but at the end of the day, it will bring you back to saying that fractional saturation is equal to kBl all over 1 plus kBl. Okay, now how will Ade explain cooperativity? Now, for Ade to explain cooperativity, you must establish, we are talking about a protein with 2 sides. You must establish that relationship between the apparent binding constant to the real binding constant. So we already said that there is a relationship in which Kb1 is equal to 2 Kb, Kb2 is equal to half Kb. So if Kb1 is equal to 2 Kb, okay, we want to look at the relationship between the first binding and the second binding. Do you understand? How do they relate? Then it means that if you substitute, you're going to have that Kb1 is equal to 4 times Kb2. Okay? Now, this last relationship will help us to interpret cooperativity. So, Ade is saying, if Kb1 is equal to 4 times Kb2, it means there's no cooperativity. Okay? It says if Kb1 is less than 4 times Kb2, it means negative cooperativity. And if Kb1 is greater than 4 times Kb2, it means there is positive cooperativity. So with these two, we can explain cooperativity, whether by step-to-step binding of other equation or that of the Hill's equation. So when we meet in class, we are going to be talking more and giving more examples on this cooperativity, because it is necessary that when you're working with a protein, that you should know exactly what is happening, the type of binding that is going on, and whether this binding, how the protein and the protein sites interact with each other. See you in